Hi, welcome to Grandparent University at Oklahoma State University. My name is Christina McCoy, and I'm here to talk to you about the Architectural Engineering program and what architectural engineers do, lead you through an activity, and just give you a little bit of perspective about what we do. So an architectural engineer is an engineer that basically works on buildings. Okay, we make buildings work. And I graduated with an architectural engineering degree from Oklahoma State University, and then I went on to be a structural engineer for about 10 years. So my job as a structural engineer was to make buildings work, make buildings stand up. We're talking about beams and columns. So I would work with an architect and figure out what made a building work. Now, I worked with other engineers. Some of them had to do with the heating and cooling of a building. Some of them had to do with plumbing. Some of them had to do with electricity. But I worked with the structure. So I'm going to show you a short video about what a structural engineer does. Now, keep in mind, an architectural engineer is a structural engineer that works just on buildings. All right? I'll be back soon. Hi, I'm back. So I hope you enjoyed the video. So a structural engineer, as the video mentioned, looks at snow and wind and earthquakes and also the weight of everything that's on the building and make sure the building doesn't fall over or collapse. So when people ask what I do, I say I make buildings stand up. And the whole process of it is pretty fun. I get to work with architects and building owners, contractors that build a structure, and other engineers to make sure that the building comes together. So when you walk into a building and you see the spaces and the structure, that all came about from a whole process of design, which people are thinking about and planning about how the building is going to work, and then construction, where people are actually assembling the building and putting it together. And so I'm a part of that entire process, and I'm going to kind of walk you through what the architectural engineer does in that whole process.
Ever wonder how tall buildings can withstand windy days? Or why bridges don't collapse when large trucks drive over them? Well, the answer is structural engineering. Structural engineers use physics and math to design and analyze the sturdiness of structures. You know, things like bridges, buildings, concert stages, and even roller coasters. Don't get me wrong. Designing any one of these things can involve multiple types of engineering, but it's structural engineering that's responsible for making sure that that structure won't collapse or fall over. You see, a structure must be able to handle the forces or loads that it's likely to experience. Take a skyscraper, for example. It not only has to support itself, but also all the people and furniture inside the building, and then external factors like wind, snow, or an earthquake. The materials and geometry that make up a structure influence how it may respond to those forces. Different materials have different properties like strength, weight, and flammability that can influence a structure's sturdiness. For example, steel is generally stronger and weighs more than wood, and different geometric shapes work better for different purposes. For example, a square or rectangular base can typically hold more weight than a triangular base. So structural engineers perform calculations to determine the best materials and shapes to use in order to build a sturdy structure. So the next time you find yourself at the top of a roller coaster, you can thank structural engineers for doing their part to make sure it's nice and sturdy.
So the best way to do that is to kind of take you through the life of a project and talk about it from beginning to end, when it's just kind of an idea in an owner's mind to where it opens and people can go inside and enjoy the space. So the first part is the big idea phase, right? The big idea, like, so if an owner wants to build, say, a school, they'll go to the architect and say, I need a school. And so the architect says, well, how many students are you going to have? What grades are you going to teach? What should the cafeteria be like? Where should the teachers be able to hang out and plan and do all what teachers do? I don't really know because my job is to make sure it doesn't fall down. So in the big idea phase, we're kind of talking about ideas and thinking about, will this work? Will this work? And just kind of getting a rough idea about what the building is going to be. So the famous sketch that you see there is by an architect called Frank Gehry, and it is the beginnings of the big idea stage of what became the building that you see on the image. The building's called Fred and Ginger. It looks like two people dancing. They're famous dancers. Um, so that's why they call it that. But really, this big idea came from this kind of sketch about what this building should look like. And then you can kind of see the structure's a little bit crazy there. The columns kind of bend and sway just like a dancer. So I'm thinking about how that's going to work is it starts at this stage. But making it work is the next stage. And that's really a big part of the design process is using math to using math and diagrams and sketches and meetings and creativity, back and forth discussions to figure out how to make this building work, how to make sure that it's going to be safe for people to be inside with all the weight of the books if it's a library, or desks if it's a school or an office, or boxes if it's a storage warehouse. So all that weight is going to be on the building, and then there's going to be wind. Some places there's earthquake too that makes the building want to go side to side. I'm trying to make sure everything is thought about. So what that looks like is I've shown a little bit here is we've got some calculations that an engineer might do. And then there's also a 3D model. And I don't know if any of you are into a video game called Minecraft where you build a 3D environment. That's kind of what it's like, but it also the 3D programs we build have a 3D environment to them, but it's not just geometry like in Minecraft. It thinks about what loads are in a structure, like what the weight of the snow would be and what the pressure of the wind would be. And it takes all those things into consideration in the geometry of the structure. So it's pretty cool. It's not the only tool we have, but it's a very powerful tool. So we use that a lot. And then there's the drawing phase. So just like a set of instructions you might get when you buy a piece of furniture or a toy that you have to assemble, there's some instructions to building a building. Before we hand it off to the contractor, we have to tell the contractor how it should get built so that all that thinking we did about how to make it work is reflected in how it's built. So you see here, I've got a sketch that I did at one point about how some bolts and welds come together. It's not always a sketch, it's usually a computer drawing. And it's like a set of instructions on how to build a building. And then build it. I cannot tell you how awesome it is to go to a construction site and see all the stuff that you've been working on. You know, you've previously just seen it on the screen or on a piece of paper, and now it's this building that's coming together and coming to life all around you. And it is super cool just to see that process and every little piece that comes together, every little column and beam and tile, every little piece of it that makes the whole entire building. It's really magical. So those are the steps in the process. And during this phase, this final phase, engineers just make sure that everything we thought about and drew is being built the way we said, the way we meant, clearing up anything that was unclear, making sure all the products are bought that are supposed to be bought, keeping everything just the way we planned it. So the whole process is really from start to finish. It can take years. Sometimes it can take months, but it usually takes years. But it's so fun to see it when a building finally opens and you can say, I did that. So now that you know a little bit about our day-to-day activities, let's take a break. Let's take a break and do an activity on our own. And what I'm going to introduce to you is an activity to make a human arch. That's right. It is a structural form that has been around for a very long time. You can see arches in all sorts of buildings throughout history. But what we're going to do, you and your grandparent are going to make a human arch. So see those two people in the middle? Arrange yourselves like that and think about the strength that you guys have working together and How you would work in a building if you were actually part of the building. If there is a third person around, have them kind of gently press on your arms and see if your arms can come down, and see what strength you gain by pressing your hands together. If you have some siblings or friends around and want to complete this activity with those two people sitting on the sides, we're going to form what's called a buttress. So yeah, that's a funny word that you're going to sit up against somebody's ankles and actually add to the strength of this arch. So without those people there, your legs might want to slide out, but with those people there, your arch is even stronger. So depending on how many people you have, you might want to give this a try. Put the video on pause and then we'll come back and we'll talk a little bit more about architectural engineers. So now that you know the whole process, I'm going to tell you a little bit of what's on our mind when we're going through those, some kind of like core principles for structural engineers. Like what are we really thinking about? When I say we make buildings stand up, when I say we work on beams and columns, what does that mean? What kind of ideas are we dealing with? So compression is the first one I want to talk about, and I've got a prop. Wait for it. I've got this Play-Doh. When was the last time you played with Play-Doh? It's super fun, right? I give this for prizes in my class sometimes when people are super smart. I throw Play-Doh at them. Sometimes. But, I don't hurt them. They like it most of the time. Who doesn't like Play-Doh? Anyway, so Play-Doh, compression. Compression is what we're talking about, right? So compression is what we're talking about. We've got this kind of squishing. That's compression, right? The squishing. I know it's not technical, but that's what it is, right? Squishing. And I like the can graphics so much. I also got a video for you guys. I know you're in for a treat here. So this little machine here is actually something that we use in engineering to test the strength of concrete. But right now it's testing the strength of a soda can. So it's doing that squishing job. And so in a building, you'll have, I talked about the weight of the books or the desks or the people inside and what they do to a building. So what we want is things not to squish, right? We don't want anything to fail or collapse. We want everything that we build to be strong enough for the squishing force. And so this compression, I hope you had your goggles on, your virtual goggles. Oh, that's fun. That is not what we want to happen in a building, by the way. So see, here's some actual buildings, some actual columns, not just a can. So if you can think of these columns like that Coke can as being squished, 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 we want to make them strong enough so they don't explode or don't collapse. And we use some code equations for it. We use physics, we use math, and we figure out what needs to happen for that to work in a building. So when you look at the columns in a building now, you can think about that being squished Coke can, this kind of column. But it's strong enough. Don't worry. Structural engineers are making sure it's strong enough. Okay, tension. It's kind of the opposite of compression, right? Instead of a squishing, it's a stretching. I've got, where are my other props? Oh, here it is. Tension, right? You guys have a rubber band somewhere, right? Somewhere. Yeah. So tension is a pulling. So sometimes we hang things, just like in this bridge, the roadway is hung from these cables, and the cables are constantly in tension. So you can see kind of like, you can think about the particles, like the little tiny particles within the rubber band, like stretching and stretching and stretching. They're not going to snap. I'm not going to snap it because that would hurt me. I don't want to get hurt. So that kind of stretching on that kind of molecular level, the tiny particles in there are stretching, and that's tension. Here's another beautiful bridge. I love it. International orange is the color of the Golden Gate Bridge. A little trivia for you. The next stress is bending. So bending happens a lot. The first two, the compression is in a column. Tension is in those cables I talked about. Bending is in a beam. So you can kind of see that granola bar being bent. And I had a granola bar prop, but I ate it. First, I did this recording. And then the recording, oh no, and then I ate it. And then the recording messed up. So I'm doing it again, but I don't have a granola bar. But just so you know, I had a granola bar. And it would bend like this. But you can see it. It's fine. You can see it in the picture. So the bending is what we don't want to happen in a beam. And so I'm going to compare it now to a balance beam. So you might have seen this in gymnastics if you're familiar with gymnastics, and you see that little girl on there, and the beam's not even like moving at all. But if that little girl was instead like a huge elephant, you might kind of see that smile form in the beam. What am I talking about, the smile? That kind of like shape of the beam. I have it on the next slide. So the parallel bars, for some reason, the inventors of gymnastics did not make the parallel bars as sturdy as the balance beam, right? And so every time that people, even those tiny gymnasts, they get on the parallel bar and you can still see the curve, like it deflects. It's got that kind of smile shape to it. I guess that's what it's supposed to do. And if you think about it on a molecular level, all the particles in the top are being squished and all the particles in the bottom are being stretched, just like compression and tension. But now we're talking about in a beam, in a building. That I'm going to show you in an actual building and not just in gymnastics. And these little beams that kind of go in between the larger supports are just like the balance beam or the parallel bar that we talked about. We don't really want them to bow, right? We don't want them to have that smile shape. And so making sure that they are strong enough to not have that smile shape is part of my job. How strong is too strong? It can get expensive if you make it too strong. But you definitely don't want to make it not strong enough, right? So shear. Shear is also something that beams experience. And it's a little bit harder to explain, but the best way to explain it is the hi-ya karate chop. It's that force that goes like this and makes things snap or crack, usually at kind of like a diagonal. So that kind of shear, that kind of force that goes straight through, not the bending, shear. That's also something that beams experience, is shear. And the next one is torsion. So torsion is twisting. So I have here one excellent example of somebody twisting and one very bad example. You can't see me twist. I'm not going to twist anymore. But these two gentlemen here are doing some twisting. One is quite better at it than the other, in my opinion. But what does that look like in a building, right? You're like, wait a minute, Professor McCoy, this is weird. Why are you doing this? Okay, so this is what a building looks like when it twists. You can kind of see where the roadway is and goes. That's not good. We don't want that to happen in structures. As you can see, this is a black and white picture. It's very old. This bridge has been rehabilitated. But what happened here is they didn't estimate what the wind was going to do very correctly. And so the roadway and the bridge actually twisted. And so as a structural engineer, I would avoid situations like this. Okay, so that completes our kind of 5-part series of what we think about, kind of like your core principles of structural engineering. So what are some example projects? I'm going to talk about a little bit about some projects I worked on just so I can give you my perspective on them. I worked on the Viking Stadium a few years back. The Vikings got a new stadium, and that was a very long design process, very long. So I got to be a part of helping design the roof. So this is an NFL stadium. It's where the Minnesota Vikings play. Their old roof collapsed because the snow was too heavy. Oh, I hate that. But the new one is very strong. Trust me, I worked on it. So we calculated the snow loads correctly, and we put this beautiful roof in that actually has a very translucent quality to it. It's a very cutting edge material. We worked with the architects to get that kind of glow. So it's kind of like, it's not glass, but it does let sunlight in. So it's kind of fun. We get to use this new material, and we make sure that every little bit in here, the trusses, oh, and by the way, you can't put many of those columns, the squished elements in a football stadium. People don't like to play football around a column. Go figure. People also don't like to sit behind a column when they're in the stands. Such a drag. So there's not many columns right here, right? They're all around the edge. So that means that this roof had to be extra strong and go extra far to withstand the snow loads and to make sure there's no columns in the middle of the field. So that's one of the challenges for football stadiums. This is a skyscraper in New York. It's called 30 Hudson Yards. The one here that you see that kind of looks like a duck, but I'm not supposed to say that. That is not a beak. It is a prow. They called it a prow. It's like a platform that you can walk out and kind of look at the skyline. It's a very high platform that it's a feature. It's not a beak. Don't call it a beak. But anyway, I worked on that. And the interesting thing about this skyscraper, it is in a show called Impossible Engineering, if you are interested. They talk all about it. That is built on this platform because they built the skyscraper over a train yard, and there's railroad tracks going everywhere. And so those columns that I talked about, the ones that take all that load to the ground, the squishing, they just had to be like placed in like random spots just to fit in between the train tracks. And so I was like, oh, we can fit a column here. Let's do that. Or here, yeah. So they just kind of like laid out this like scattered grid of columns, and then they built a huge building on it, like a 73-story building on it. And figuring out how that load path worked and how all those how the weight from the people in the desks and there is a lot of offices, some shopping and some condos all in this tower. So all different kinds of loads going in and finding their way to the ground through this big skyscraper. And then, fished in between these train tracks all the while when it cuts to the ground. So it's pretty challenging, pretty cool. All right, so this final building I wanted to talk about is another one I worked on. It is called the Shed at Hudson Yards. It's near the skyscraper that doesn't look like a duck at all. The Shed is kind of like this. It's a museum, but it is a very free-form museum that can accommodate performances and concerts, not just art. It's designed to have an open concept and have different exhibits come through. So anyway, there's a plaza on one side over here, and this part that kind of looks like a covered wagon, but also I'm not supposed to say that. So let's just call it, I don't know, a shed. That's what we're supposed to call it. So that shed can be over that glassy part, or it can come out on wheels over the plaza so that they can use a or they can use that plaza for a concert or like a dance performance and have it covered by the covered wagon, the shed. And then when they're done with it, they can put it right back on top of the other building. So, and make it an open air plaza. Pretty cool, huh? So it's like this whole part of the building that moves on wheels. And this wheel, I should have put a little guy here. These wheels are 6 foot in diameter, so they're taller than me. You don't know me. You don't know how tall I am, but trust me, I'm not that tall. So it's pretty big, and there's one right here, one right here, and one right here. They're called bogies, but they're really just wheels. And they're also on this platform that is above some train tracks. So some pretty interesting engineering went into all of that as well. It was really fun. So those are a few examples. That concludes that part. And now let's build something. Yeah? Yeah, I want to build something. So let me give you little parameters. I hope you have the supplies. Okay, so here are the supplies. Paper and pencil, because before we build something, we're going to think about what we're going to build, right? We're not just going to willy-nilly start building. Oh, no, no, no. We are thoughtful engineers. So we are going to sketch it out first. Also 100 toothpicks. I counted mine. Did you count yours? I'll pause. I'll wait. You can pause it. Okay. A bag of mini marshmallows. You are not limited on the amount of marshmallows you can use. Make sure you get the mini ones though. The big ones are just, they're too big. Because the toothpicks are, toothpicks are tiny. So mini marshmallows, you can eat them afterwards, but don't eat them yet because you're gonna need them, like me and my granola bar. Like, I probably shouldn't have eaten it, but it was so good. So take it from me, use your marshmallows, make sure you get on what you want to do, and then you can eat them. And then some books, because the books are going to be our weight, and a scale. You don't have to have the scale, but if you want to be scientific about it, I recommend it. Okay? Okay, so here's what we're going to do. I've done this before. This is my picture. So see these young women? They have made a tower out of toothpicks and marshmallows. That's the only materials. And then they're putting their books on it as a weight to load test it. That's what we're going to call it. We're load testing our towers. The goal is to make the tower withstand as much weight as possible. The time limit is 20 minutes. I suggest you spend at least 5 minutes sketching, but you're going to use every bit of that 15 minutes to build too. So make a plan first, sketch it out, and then, sorry about that, and then build. You can only use the supplies you've been given, obviously. Okay, so top tips. Take it from me. I'm a structural engineer. Triangles, triangles, triangles. I know that you've seen some rectangles in my presentation. It's true. Sometimes we use rectangles. A lot of times we use rectangles. But for this exercise, triangles are king. That you're going to fail it if you have too many rectangles. Just stick another one in there. Cut that rectangle across the middle just like you're slicing a sandwich, and make triangles out of it. It's going to make your structure a lot stronger. And also, trust me, I've done this exercise before. Sometimes you poke your marshmallows too many times and they become like Swiss cheese. You are not limited on the amount of marshmallows. Double those babies up. Marshmallow on top of marshmallow. It's fine. And then I would say focus on stability over height. That's just a tip from me. You can do what you want. It's your marshmallow toothpick tower. If you want to build it really high, go for it. It's going to be beautiful, I'm sure. But when you put a book on it, well, you know what's going to happen. So I would say focus on making sure it's strong and robust, and then we'll get it off the ground, right? Okay, that's all I got. So I'm going to turn this off, and I'm going to build mine. I want you to build yours, and we'll come back and see what it's all about. Okay? Hi everyone, so we're back. So we made I'm going to admit mine is more like a platform than a tower. But hopefully you've got a construction a little bit like this. Maybe it's completely different. That's fine too. There's more than one solution to these problems. So as I mentioned, I love triangles for this exercise. So I made a nice sturdy base with a bunch of triangles. And then I built up with it and I made triangles. See all the triangles in there? Oh, that's not a right triangle. Lots of triangles. Okay, so let's see how much this can weigh, or this can hold. I've got my scale right here. Okay, I think we're ready to go. We're going to start with something easy. We're going to start with the structural basis of architecture, okay? How much does that weigh? It's not even anything on my scale, so it must be less than a pound. Let's get some more on there. All right. Okay. So here's 1.6 pounds. All right, so we're going to have, and by the way, I would totally recommend these, maybe when you're in high school. This is Why Buildings Stand Up. I love it. It's by Mario Salvadori. It is a good introduction to architectural engineering. And then there's also Structures, or Why Things Don't Fall Down by J.E. Gordon. Okay, let's try this. Okay, I got my corner collapsed. I'm going to try to fix that. Just going to cheat a little bit because I want this to work. Okay, luckily I've got some marshmallows doubled up there. One of them was kind of Swiss cheesy. Better. Okay, much, much better. Okay, so we got these books here. Let's just use the two little ones. All right. Flat already. Oh my goodness. What are we going to do? All right. So as you can see, we've got a little bit of squishiness in the structure. Nothing, but it did completely collapse. So what I'm going to do here, remember the arch exercise? And we had two people in the arch, and then we had those buttresses by it. So what my structure is trying to do right now is kind of widen out and flatten. There's nothing keeping it together. So let's make some buttresses. Put some other books up here to keep it from flattening. All right, we've got some nice sturdy books on the sides. Maybe that's a solution. These are some sketch journals. By the way, I also recommend these sketch journals. They're Moleskine brand, but anything you want to carry around with you and start sketching the world around you is a great, great way to get started. Okay, so let's try it again, but now we've got buttresses. Hey, not bad. It's holding up. Yep, I'm making sure it's all on the structure, not just the books. Get another one there. Oh, it's starting to give. Yeah, I think it gave. All right. Now we've got this nice pancake of a structure. Oh, my poor little structure. It's going to be tasty though, right? I don't know. I might just throw these away and eat what's left in the bag. But, so, I hope you had fun. I hope this was a great activity for you guys, and I hope you got to learn a little bit about architectural engineering in the meantime. Thanks a lot, y'all.